Hello everyone, welcome to episode 5 of Qiskit Developer Coding Series presented by QuantumGrad. This series helps you prepare for this professional certification exam. I am Abha and let's get started. Today let us solve question 5 from the Qiskit Sample test. Here's the question. Which code fragment will produce a maximally entangled state or the bell state? And we have been provided with 4 options. For a quick introduction to the bell states, check the link in the description below. This is the code. Let us first import all the necessary packages. We import Quantum Circuit, Air, and Execute from the Qiskit library, and we import all the functions from the Qiskit Visualization library. I will explain what all these functions do in just a moment. Let us first build our required circuit. We have a quantum circuit called QC bell with 2 qubits and 2 classical bits. Let us apply a Hadamard gate to the first qubit and a seed knot to both the qubits, with the first qubit being the control bit. Now, measuring the qubits onto the classical bits, this is what our quantum circuit will look like using Matplotlib. In order to execute this function and see how the ideal quantum computer handles it, let us use the Quantum simulator. This simulates an ideal quantum computer with 100% fidelity that, as you know, is not yet achieved by our present-day quantum computers. We need to run the circuit multiple times to overcome the probabilistic nature of quantum measurements. The number of times a circuit is executed is called shots. We pass this task to the execute function, its parameters being the circuit, the backend, and the number of shots, that is 1024 in this case. To retrieve the results, we use result.job, and to get the counts, we use result.getCounts. Now let us see what our counts are. As you can see, we get 1 1 494 times and 0 0 530 times. Plotting the histogram data shows us the counts, and as we know, the simulator is error free, that is, it's noise free. So this histogram here shows us the results under ideal conditions when there is no noise. You can see the counts are only on 0 0 and 1 1. This is the bell state, which simply says that if you have 2 qubits which have been entangled using this, and then you take the qubits miles apart from each other, if you measure the first qubit as 0, you're definitely going to measure a 0 on the second qubit. Also, if the first qubit was measured 1, rest assured that the second qubit is also 1. This is a phenomena that blew Einstein's mind. Here are the 4 types of maximally entangled states for 4 different types of inputs. This is the first example where we have the input 0 0. On applying the Hadamard and a C0 gate, we have an entangled state of 0 0 and 1 1. This is what a state vector looks like. This is the second input. We apply the same combination of gates H and C0. Let us see what a state vector looks like here. I will make a mention here that we are using the state vector simulator here from the Air, and we're using it by using the get_backend function. As you can see, this is our state vector, and our result is an entangled state of 0 0 and 1 1. The only difference between this and example 1 was that we have a negative phase here. This is what a Q-sphere will look like. Now, Q-sphere is imported from the Qiskit Visualization library, and the color of the Q-sphere shows us the phase of that particular state. Let us see our results for input 1, 0. Now, I would like to mention here that we are going in the most significant bit to the least significant bit order. That is, qubit 0 here is the least significant bit and qubit 1 is the most significant bit. So 1, 0 in our input is actually qubit 1 in the 1 state and qubit 0 in the 0 state. We have this circuit. And this is what a state vector looks like. It is an entangled state of 0, 1 and 1, 0. Lastly, we have 1, 1 as our inputs. This is what a circuit looks like. We have an entangled state of 0, 1 and 1, 0. However, this time we have a negative phase, as can be seen in this Q sphere right here. Now that you know all the Bell states, let us tackle this question. Let us see what does option 1 look like. As you can see, we have the input as 1, 0 and we have our H and C naught combination, and when we run our state vector code, you can see that we have an entangled state of 0, 1 and 1, 0. Therefore, this is our maximally entangled Bell state. During the exam, select this option and move on. But right now, let us discuss the other options. Let's see option 2. This is our circuit. As you can see, our combinations order is reversed. Let's see what this results in. As you can see here, we don't have a maximally entangled state. That is, no matter what result you have for the first qubit, your second qubit will always be in state 1. Let's evaluate option 3. Here we use a control Z gate instead of a C naught, and this is the state vector resulting from it. Again, this is not a Bell state, because no matter what result you get, the first qubit, the second qubit will always be in state 1. Finally, we have option 4. Here we just have a Hadamard gate applied to each of the 2 qubits. Here, we are not creating any relationship between the 2 qubits. That is, you can't predict with 100% guarantee what the state of the second qubit will be given you have the state of the first qubit. That's it. That solves our question 4. But now I would like to also provide you with a quick additional note. We also have a 3-qubit Bell state, which is known as GHZ. H on the first qubit here and C naught on qubit 0 and 1 and qubit 0 and 2. This state vector here is a maximally entangled state of 0, 0, 0 and 1, 1, 1. That is, if we measure the first qubit in state 0 and the other 2 will also be in 0, and the same thing applies if we measure the first qubit in state 1. Finally, we have solved this question. Do feel free to drop your doubts in the comment section below. If you found the video helpful, do give it a thumbs up and subscribe to QuantumGrad for more such videos.